Okay, this is Physics 1B for November 30th. Today we're talking about waves. We're going to learn about mostly the three topics that are written at the top here. We want to understand what is a mechanical wave and how does it work. And then we want to understand what happens when you have multiple waves traveling through the same medium at the same time. So we can understand the phenomenon of interference as well as of superposition. And then the final part of the class, we'll talk about standing waves. And if we have any time left at the end, we'll also talk about sound waves and sound intensity. So I guess the goal of today's lecture is by the end, you should be able to understand what a wave is, as well as what the difference between a wave that travels, what we call a traveling wave, versus what's called a standing wave, which is kind of a special case that shows up all over the place. You should also understand, to some extent, I would say, how stringed instruments work after today. That is to say, things like guitars, violins, as well as, if we get there, we might learn about like the wind instruments like flutes and oboes and things like this. Yeah, so all of these things have one thing in common. They all have waves associated with them. And so let's get started with that. Let's talk about what waves are. All right, so a mechanical wave is something that requires basically two things in order to work. So it has two components. It has, number one, it has a medium. And then the medium itself has to have some kind of connection between its parts. Examples of mediums could be things like water. I'm sure that everyone in here has seen waves in water, whether they be waves on the ocean or the ripples in a pond. Those are both examples of waves. The medium could be something like a rope, a string, a cable, something like that. Examples of this would be, as I said, the waves that are produced on a guitar string, or if you've ever taken like a long hose and you've like kind of whipped the hose to send a pulse down it. Same thing with like a long cord or extension cord of some kind. Other types of mediums could be air. In the case of sound waves propagate through air, but they don't propagate through a vacuum. This is part of the reason why a medium is essential for a wave, is because in order for the wave to travel, it has to have something to propagate through. We use the word propagate to describe what happens when the wave travels through the medium. What other kind of waves there could be? You could have like seismic waves, which travel through the Earth's crust. So the Earth itself could be a type of medium for a wave. What else? What do you guys think? Are there other examples of types of waves you've seen? And what kind of mediums would they have? Medium just means some kind of material. So electromagnetic waves are a special kind of wave that we won't really discuss in detail today, but they happen to be unique in the sense that electromagnetic waves are the only wave that we know about. Well, yeah, let's leave it at that. They're basically the only wave we know about that doesn't have a medium. There's also gravitational waves. And then there's the idea of the quantum wave function, but still, those are... But yeah, so electromagnetic waves or light is another example of a wave. It is not what we call a mechanical wave, though. It's its own kind of wave. As the word you used is the right word, electromagnetic. Heat. So people talk about heat waves, but that phrase is kind of different from what we mean by waves, right? When people talk about a heat wave, they just mean that it's getting really hot, right? There's like a wave of heat coming through a region or something like that, but it's not exactly a real wave. What other kind of waves are there? Well, if you think of any other examples, let me know. Okay, so the second thing you need for a wave is you need a disturbance. Those two things will produce a mechanical wave. A disturbance in a medium that's basically what a mechanical wave is. In the case of water, that disturbance could just be like a rock thrown into a pond. Or it could be like water dripping or something like that. Or it could just be your hand. You just hit the surface of water and it will the wave will propagate out. We can see this with this little device right here. So let's look at here. We'll go to water waves. So what we can do a lot of things here. Let me just reset everything. So I want to talk about two different kind of waves first. There's waves that are kind of like pulses, and there are waves that are periodic, okay? And I think we generally think of the periodic ones, but the pulse ones are much easier to understand. So I'm going to start off by just sending one pulse out. So this is supposed to be like water here. And that's like a ring that's formed when you just put one drop of water. So the medium in this case is this blue thing right here. It indicates kind of what's called the crest of the wave and the trough of the wave by colors. So the trough of the wave is indicated by the kind of dark line. Oh, you can't see this? Really? Maybe it got switched whenever I lost the... How about there? Can you see this now? Looks like you can. Okay. I'm sorry about that. Okay, going back. So this is supposed to be like a trough of water. Except it doesn't have walls, I don't think. I think that just the waves don't bounce off the walls in this trough. So it's kind of like a picture of water that kind of goes off into infinity. So a single pulse of a wave would look something like that. So the crest of the wave, or the top of the wave, is indicated by this lighter color, and then the dark color represents the trough of the wave, the kind of minimum. So you got a maximum and a minimum to the wave. So each one of these would be a single pulse for the wave. Okay. I think one common misconception about waves is they need to be periodic. They don't have to repeat themselves. A wave is just a disturbance in a medium. That's it. Okay, we can also make this disturbance periodic by doing this. And then it'll just perpetually lead to drips. This probably looks a little more like what you see when you actually throw something into a pond, though, right? Because, I mean, I don't know. Tell me what you guys think. If you were to throw a rock in a pond, would it look like that? Or would you see a lot of little ripples? What is y'all's experience with that? Does that question make sense? Do you see just this single perfect pulse? You see a lot of ripples, right? So you really kind of see something that's a little more like this. Right? You see this kind of repetitive pattern. The ripples tend to get kind of like lower in amplitude as they go out too, right? Now we can do things like we can increase the frequency here, so we can make it go faster. By increasing the frequency, we also change some of the properties of the wave. There's basically going to be three properties to waves that we're going to describe. There's frequency, there's wavelength, and there's velocity. They're all connected to each other. The velocity is equal to the frequency times the wavelength. So to understand what the wavelength is here, what we can do is we can kind of grab this little piece right here. The wavelength is basically the distance between either two troughs, like here, or it's the distance between two crests, like, I mean, it's moving, so... Oh, I can pause it, right? Here, let's pause it. So we could describe the wavelength of this wave by either measuring the distance between the two peaks, or crests, which looks like 1.7 centimeters or so. Or we could measure that by measuring the distance between the two troughs, which you can see is pretty much the same length here. Right? So that's what we call the wavelength. In this case, it's 1.7 centimeters. The wavelength, however, depends specifically on the frequency. The velocity of the wave is determined by the medium itself, as we'll learn. So since the velocity is equal... Here, let me write the equation real quick here. Oops. So these are the symbols. We use lambda is what we use for wavelength. We use F for frequency. Sometimes people use the symbol in nu, like the Greek N. That's what we use for frequency. Wavelength is measured in meters. Frequency is usually measured in inverse seconds, or the SI unit for this is called hertz, named after the person who first, Heinrich Hertz, I believe is his name. In 1889, he produced the first electromagnetic wave, which is, again, it's not a mechanical wave, but it's a type of wave. And he effectively is the person that Well, we'll just say he proved that light was an electromagnetic phenomenon in a way, where he verified the theory that Maxwell had proposed that light was an electromagnetic wave. Okay, so you've got frequency and you've got wavelength, and then you've got velocity. And the relationship is that the velocity of the wave is equal to the frequency multiplied by the wavelength. That's a really simple equation, right? So if you increase the frequency, but the velocity, okay, I'll just mention right here, right? The velocity is dependent on the medium. In general, if the medium is really thick and dense, the velocity is going to be slower. And if the medium is kind of loose, like air, the velocity might be higher. As an example, waves on strings might have velocities of orders of like 20 meters per second, but waves in air, like sound waves, you guys probably know, are really fast, right? Sound waves travel with a velocity of about 343 meters per second, which is something like 720 miles an hour. It's extremely fast, right? And a lot of the reason for that is because air is a very rarefied or not dense medium, whereas liquids and water and things like solids like strings are pretty thick by comparison. Their mass density is really high, right? So if velocity is equal to wavelength times frequency, and I tell you the velocity is really, I mean, it's dependent on wavelength and frequency, but the velocity itself is a function of the medium that we're talking about, then what happens as we increase frequency? What has to happen to the wavelength? If we make the frequency bigger here, or if we make it smaller. Let's do bigger first, though. So let's say we take our wave. Let's go back to a medium amount of frequency here. Let it start dripping. And then let's measure our wavelength by pausing it. So you can see that it got bigger, but if I increase the frequency here, frequency and wavelength are inversely related is what Kenny's saying, yeah. So if I take the frequency and I raise it up to maximum right here, what's going to happen to the wavelength? Is it going to get smaller or bigger? So if I increase the frequency, smaller. That's right? Let's check that. We should be able to pretty quickly see this, that the waves should now get closer together. That's what you can see that these backward waves here in the back are kind of closer together. And now again, if we pause it, you can see pretty clearly that the wavelength is shorter now than our original measuring stick here. And now the wavelength looks like it's about 1.9 centimeters or so. Right? And as we increase that, it goes up as well. And we can do something else here. We can also show something about how the way that this wave is working in this particular case, we can kind of show that it's basically a sine wave by using this little meter right here. This measures the water level, okay? And we can see that as we kind of go across this, that this is the low point of the water, this is the higher point of the water, right? And that as you go across it, if you look at that little ball on the right there, it's basically, popping up and down, as you might expect. And then if we turn this on, and we just let it go, then you kind of see the waveform as if it was viewed from the side, kind of like a y as a function of x and t, so to speak, that we're showing right here. And it looks like a kind of perfect sine wave, basically, right? Now, a lot of that is because of the way that this wave is being produced. In fact, all of it really is because of the way this wave is being produced. If we were to switch to this little piece right here, then you'll see that the waveform goes away. And now if we use like a pulse, now while the pulse goes across, it's going to make a little sine function, right? But that's it. It just kind of dies out. I want to emphasize as much as I can that this is as much a wave as the other thing we were looking at. Like, that's still a wave. It's a disturbance. This disturbance propagates through the medium due to the fact that the pieces of the medium are connected together. And so they're both waves. This is a wave, and this thing is a wave as well. They're both waves. Okay, anyone have any questions so far? All right. So, all right, let me look at my notes and make sure I'm not missing anything here. Okay. This, by the way, I should say, the velocity equal to wavelength multiplied by frequency, this is really, this is mostly going to apply to what are called periodic waves, the type of waves that are repeating themselves. All right. One other thing I want to mention about waves is that in general, Waves tend to transport energy, but they don't really transport matter. Generally, the medium itself basically stays in the same location. And this is mostly because the medium doesn't tend to move. And I guess move is probably the wrong word here, because obviously when we look at the wave here, this wave was moving, right, up and down. It just doesn't move left to right. And so, as a result, the medium doesn't, you might say the medium doesn't translate, I guess is the best way to say it. Kind of tends to stay in the same place. Your book has a picture here. I don't know how good this picture is. But this picture tends to describe the different types of waves you can have. So the wave we were just looking at with the water, that's what we call a transverse wave. So there's two types. There's transverse, as indicated by the first picture here, and there's longitudinal. These are the two types of waves. You can have waves that are combinations of these two, but transverse basically means that the pieces of the medium move perpendicular to the direction of the wave motion. The parts of the medium move perpendicular to the wave velocity, and in a longitudinal wave, the parts of the medium move parallel, basically. That's kind of the base definition. Right, so the first one here that they're using as an example is the motion of a wave on a string. So someone whips a string, and they do so by moving the string up. That causes the pulse on the string to basically travel to the right. The individual particles basically only go up and down, like this. But the wave itself moves to the right. The velocity is to the right. So that's what we call a transverse wave. For a longitudinal wave, what they do here is they have a fluid. This comes back to kind of some of our heat stuff, where you have like a piston that goes back and forth here, but the container is fixed. All right, so the container is like the top is closed and the bottom is closed, and the liquid basically completely fills it with a fluid. This wouldn't work very well for water, but it might work a little better for air because air can be more easily compressed. But in this kind of wave, where you're basically oscillating this piston back and forth and back and forth and back and forth, it's going to cause the particles of the fluid to move left and right like this. And what's going to happen is you're going to have regions where there's basically like kind of high density. And then there's going to be places where, like right here, where there's low density. And those density fluctuations are going to be what the wave is, basically. For each of these, we could talk about examples. And for a longitudinal wave, the best example is, the most common example is sound. Except this is really hard to visualize. It's kind of hard to visualize. I think a simpler example that's easier to understand is a slinky. Do you guys know what slinkies are? Certainly you do, right? Or is that just too old? Do you guys know when I just say slinky, do most of you know what that means?
Yep. Love this as a kid.
Okay, so they still sell these things. So it's kind of hard to do with like a commercial slinky, but a slinky has, there's no way I can draw this. A slinky is made up of like parts that are kind of like coiled up like this, right? And bear with me as I try to draw a horrible slinky. Now, what you could do with a slinky is you could kind of like lay it out on the floor or hold it between. The best way to do it is have like two people hold it, basically. You have one person hold this side, and you have one person holding this side over here. And then what you can do is you can kind of like pinch the slinky. So you could basically pinch a piece of it over here, so like squeeze it together so that you get a little like compressed up coils like this, and then let go. And what will happen is that when you squeeze it, there's a picture of a slinky. That's nice. You could do it with that kind of orientation of the slinky too, but the idea is you compress a piece of it and then you'd let go. And what would happen is that a longitudinal wave would propagate down here. You'd have pieces where the slinky was really compressed, and then pieces where the slinky is not compressed, and then more compressed, and then not compressed, and then more compressed, and then not compressed. And this would all happen by simply squeezing one end of it and then just letting that propagate out. And that would be your wave. That's a longitudinal wave. This is how we just demonstrate this in the laboratories. We've got a really, really long, skinny slinky, and you just hold it out tight, and it kind of droops a little bit like a power cable. Like a, yeah. And you just squeeze a piece of it, and then let go, and a pulse will basically propagate out. And it'll kind of be these, like, it'll just kind of go in and out. Like this one little piece right here where you squeeze it, it's going to expand, and then it's going to compress, and it's going to expand, and it's going to compress. The pieces of the medium aren't going to go anywhere, but there will be a pulse that basically travels down the slinky like this. Hopefully you can visualize that. And maybe if you have a slinky in your house, you can kind of try it out. Okay, and this all works because the pieces of this slinky, the slinky is the medium, they're attached to each other. So if you try to disturb a piece of it, there's going to be a little pulse that travels along. Okay, what are some other examples of longitudinal waves? Anyone know? A spring. Yeah, so the slinky is basically a spring anyway, right? So yeah, I think it's the same. But yeah, the kind of springs would work too. I don't know another example of a longitudinal wave. Maybe you all can use the powers of the internet and see if you can find something for us. But usually these are the only two that I can think of as sound and slinky for the longitudinal waves. I'm sure there's more. Like I said, there's things that are combinations of both of these, like earthquakes, or a combination of transverse and longitudinal. Okay, transverse waves. These are the much more common type of waves. And examples of transverse waves. We've already kind of given some of them. So waves on a string, waves in water, I mean, I'll put this in here, although it's not exactly, this is not part of this course, but light is another example of a transverse wave. Yeah. What are the other ones I mentioned at the beginning? Water, string, earth, air. So this is going to be, earth is going to be like a combination wave. So the combination wave is something like this one here on the bottom, where you have a combination of motion up and down and left and right. Now, the difference between B and C here, maybe it's not obvious, we should talk about it, is that in part C, the waves on the surface of a liquid, the container's open on top. So that when this person on the right, or on the left here, when they push on the wave can actually rise right here. And the effect of that is that if the person keeps pushing back and forth on the left-hand end, then the wave pulse that goes through, if you look at an individual particle in the medium, it's basically kind of going in circles. It's kind of hard to imagine, I think. But this would be like when you see a wave on the ocean that's kind of traveling in and crashing on the shore, this would be the kind of wave that's happening there. Like deep out in the ocean, though, I feel like if you go deep enough in the ocean, the waves just basically go straight up and straight down. Would you all agree with that statement? Maybe I'm wrong about that. I'm just talking about from what I've seen, and I don't know if that's completely accurate. Like, when I think of a wave on the ocean, do you guys know what I'm talking about? If you go deep enough out on the ocean, where you get these swells, where the ocean basically just goes up and down and up and down. Do y'all know what I'm talking about? Getting no response. I'm assuming you're not. Maybe I need to explain it better. I don't know. Anyone have any experience with that? Like being out on a boat deep in the ocean where you get these big swells? Yeah, like when you go fishing. You're out deep out in the ocean. I'm specifically... Yes, that's kind of my question, Andrew. Is that just a transverse wave, what I'm describing? Or is it like this? I guess that's my question. Which is it? I mean, is it a transverse wave or is it a wave that's doing something like this? I don't honestly know. I just know that you think it's more like the combination right here. I mean, the reason I mention it is because like if you get far enough out on the ocean where you're not near enough to the shore, the water 100% definitely. I mean, it can be still, but if there's any like wind or if there's any motion of the waves at all, what tends to happen is that like if you're in a boat, the boat basically you'll rise up with the wave and then you'll fall back down. You'll rise up and you'll fall back down. But it often doesn't feel like the water's going anywhere. It doesn't feel like it's like this. It feels like it's more like the first one. But it could be the case that it's exactly what they're describing here on the very bottom, where you have a combination. Anyway, something to think about. If you go out on like a deep sea fishing trip, or if you go out on like a boat that's like traveling to some island nearby or whatever, next time if you are out on the ocean, try to pay attention to what the water does. It's very interesting. I've definitely been in like storms out in the ocean down in Florida where the waves were going like 12 feet from top to bottom, like kind of like this basically, where from here to here it was like 12 feet and the water just basically goes up and down and up and down. It's like being on a roller coaster. That's how people get sick at sea too, because you're just constantly moving. The water never stops. This was crazy to see though, to where like you're literally in a boat down here, right? And you cannot see outside of the water. Like you look left and you look right and you just see the curl of a wave. But it's interesting because as long as the wave doesn't break over you, it's not a big deal. But you just ride up and down and up and down. That's why I'm saying I think it's less like this and more like the top one, just because like if the wave crashes, then it becomes more like the bottom one. But I don't know. Okay, so these are all just kind of conceptual examples of waves. Waves transport energy but not matter. I think I've covered all the basic kind of topics of these things. Wavelength, frequency, velocity. So what we want to do now is to... Let me just see something real quick here. Okay, I didn't think I had a problem, like a example problem for that stuff. So the next thing we want to do is, because this is physics, we've got to throw some math in there. And we want to kind of come up with a mathematical description for a wave. And specifically, this book likes to start with the mathematical description of a sinusoidal wave. So the sinusoidal wave is going to look something like this. We're going to use this picture to describe it. It's a really big picture. So what do we have here? Actually, let's start off with an actual example of this that's a little more easy to see. Here, we'll do this. Okay, so we've got a string here which is represented by all these little balls, and they're kind of just there so you can kind of visualize what the string is. But this is definitely the way that a string behaves. So what we can do here is we can put a pulse on this by doing that right there. I can basically just, and honestly, if you want to play with this yourself, which I often think is a pretty good use of your time while you're sitting in classes like this, if you want to just play with this and see what you can do with it, go for it. But we can see a lot of features of waves with this thing right here. One feature that this shows, and this is something that if you've ever taken a hose or an extension cord and tried, you can do the same thing. You lay an extension cord on the ground and you just like whip it like that. What do you notice about the amplitude of the wave? And I haven't defined amplitude yet, but hopefully you guys know that amplitude is the height of the wave. What do you notice happens to the amplitude of the wave as it travels along this string? Does it stay the same? It decreases, yeah? Okay, so it's decreasing in this case because there's some energy being lost through this thing that's called damping. You can actually completely get rid of it by clicking over here on none. It's completely unrealistic, like it doesn't happen. And then you see that the wave is basically just this perfect pulse, right? That travels like that. Now, we can also produce what are called sinusoidal waves. If I oscillate this up and down just perfectly, like this, then you can basically produce a sinusoidal wave. So the left end is just oscillating up and down. And, We can make that a little more clean if we do this. So there we got kind of a perfect sinusoidal wave, just traveling off into nothingness over here. Now the reason why I'm making it so that there's this open door over here is because if we, for example, do this, I'm going to put damping back in or this will get crazy. Then what happens is that wave kind of kicks back towards us at the end. All right. And if you do it enough, you start getting some craziness going on. All right, so if we do no end, this is more consistent with what we want to do. So this is the type of wave that we want to describe. There's a pulse wave. We want to describe this kind of wave now. This is going to be what we call a sinusoidal traveling wave, and the one that we're going to talk about is going to have no damping. Although describing damping tends to be pretty easy, as it turns out. But that's the type of wave we want to describe. And you can see we call this a traveling sine wave because if you just look at it, you can see that there's a wave that's basically traveling, especially if you just kind of look at, if you ignore what's happening on the left side, you just kind of look at this region of space, like right over here on the right, you can definitely see a sine wave that's just traveling past your eyes constantly, right? It's like a fixed waveform that's just traveling at this fixed speed. Yeah. So we want to describe this motion, and we want to use a function to do so. And the way we're going to do that is we're going to describe a function of y, x, and time. So y is going to represent the height of the wave at any point right here. And this is showing what the wave looks like at different times. And it's relating it to period, right? So it goes through one full period. And it's saying, like, at t equal to 0, this is our waveform. And then at t equal to 1/8 the period, it's moved a little bit. If we come all the way down to this is half of a period, the wave will have moved exactly 1/2 of the distance. You can kind of see if you compare t equal to 0 right here, and you compare that to t equal to t over 2 right here, and we want to just look at one point really, because it gets kind of complicated if you try to look at too many points at the same time. Notice here at t equal to 0 that this point is at a minimum, and here it's at a maximum. Right? If you look at the next point, which was at a maximum, it's now at a minimum. And if we follow this thing all the way through to the end, we get back to the original point again, right? You should see that the very last waveform right here, if you look at the points between here and here, up to this third red dot, it looks exactly like the first waveform. So this means we know that it repeats. The wave advances by one wavelength lambda during each period t. And that's what the little blue lines are here are designed to show, is that our wave started right here, and now it's moved to here. I feel like they may be, like, what I would say is that, like, that little waveform that goes from that point to that point to that point is now at this point right here. It's traveled forward one wavelength now in a time period t. That's probably not that surprising because the velocity of the wave is given by lambda times f, but f is equal to 1 over t. So the velocity could also be written as just lambda divided by the period. The period is the time for one oscillation. The frequency is the rate of oscillation, right? Okay. So we've set all that up, and we still want to come up with a mathematical description. Our goal here is to describe how the wave moves as a function of x and t. What does the waveform look like? This is going to be what we call the wave function. All right. So the way we're going to go about doing this is we're going to say that if we just look at what's happening on our string right here, if we wanted to describe the left edge, so the point right here, this is going to represent x equal to 0, by the way. That's x equal to 0. Suppose that we wanted to describe what that point looks like. So that point is at the value of x equal to 0. We're describing y of x and t. So if we wanted to describe what the left edge of the string is and what it's doing, we would be looking at the point x equal to 0 and figuring out what that piece is doing over time. Now we can see from the picture that we were looking at here, where this point is oscillating up and down, if I wanted to describe the motion of just that left point right there, would you all agree that we could just use a sine function or a cosine function to do that? That just that point right there, the way that it's moving, could be described by a sine function over time, or a cosine function. And we could write it like this. We could write it as a multiplied by, this can be sine or cosine, it doesn't really matter. We're going to use cosine. Cosine of omega times t, where omega represents the frequency, the radians per second, and obviously t represents time. If we let time evolve, let it go from 0 to 1 to 3 to 4 to 5 seconds, and just let it increase, that's going to describe what this right here will describe what the left edge of that string is doing. I'm going to stop right there. Does that make sense to y'all? When you look at that equation right there, A is going to represent the maximum and minimum values of y, right? It's going to represent, effectively on our picture right here, this would be y equal to A, and this point down at the bottom, for example, would be y equal to negative A. So you're going between positive A and negative A always. But does that seem right to you? Does that make sense? The left edge of the string, that its motion would be described by this. Okay. And again, for me, I have to see this in motion to understand it, because that function that I wrote down has time in it, right? And time is constantly evolving. So I think if you look at the left edge of this, you probably agree that it's moving up and down like a cosine function. But if you just pause it in time, it's a little harder to understand. So it's nice having that, because just looking at this picture over here, this isn't as obvious to me. When I look at the animation, this makes sense. That's what the left edge of the string is looking like. Okay. Now, we know that this disturbance is propagating along our wave with a constant velocity, right? So we know that the pulse or the disturbance travels with a constant speed. Can you guys hear that cat? No, I don't think you can. Constant speed v. So if we want to understand what's happening at another value of x right here, right? So we specifically were looking at the left edge of the string, which is where x is equal to 0, right? So that's our x coordinate, is x equal to 0 right there. But we need a function that has x in it as well. So in order to understand that, what we can say is that since the disturbance travels with a constant speed, if we look at a point x, now this is just going to be some arbitrary point x on our string, as referenced by the fact that x is in this direction here. So we could come over to some new point, like for example, here, let me erase what I wrote right here. So just remember that the max and minimum are positive and negative a on our graph right here. So if we were to come to a new point, for example, like here, that has a coordinate that we say is x, which is an arbitrary point. And if we thought about that as being the point, like, imagine what happens when, here, where's a good example of where this happens? I think it's here, right? Here. Yeah, it's really hard to tell on this. If we look at a point, let's say, for example, that we were looking at the time when the curve was at a maximum right here, and we think about a point that's to the right of it by some distance here, then we can say that those two are going to have a relationship to each other. And the way it's going to work is that the motion of point x at time t where this t might be the same as some time here, should be the same, or is the same, as the motion of x equal to 0 at a time t minus x over v. Oh, I left something out here. No, I didn't. That's right. That's what we want to write. Okay. Does this make sense? First of all, let's remind ourselves of something that I think sometimes people forget. In Physics 1a, we talk about uniform motion, right? And with uniform motion, we get the relationship that the distance that something travels is equal to velocity multiplied by time, right? We can invert this to say that the time would be equal to the distance divided by the velocity, and that's really all we're doing down here. Right? If we look at the motion of a point x that's some far point in the future, that motion, this is the thing about this I think that's really hard to understand. It's the motion that matters here. Right? If I want to find the place on the string, and we can see this really easily here, so we should do this on this part right here. Let's pause it right there. If we think about these 2 points, so we think about the point right here where the thing is at a maximum, and we think about the left edge where it's at a maximum now too. This is what we're saying. I'm just gonna, we can do reference line. That's not, wait, can we do up and down reference line? Nope, we can do rulers though. Here, let's set this up. Let's just put the 0 right here. All right, and I really don't need the rest of these things. I don't need this, and I don't need this. So what I want to do is I want to look just at that point 0 right there. Actually, maybe it makes more sense to do this. So what is the point? It's like 4 and 4.2 or something like this. So here's the idea of what we're saying. So we move to a new point, x. This is our point x right here. That is a certain distance away from the original point, right? And then we say the motion of that point, right, is identical to the motion of the point on the left. I feel like this is really hard to see, but I'm just going to put my mouse right here. So you somehow have to imagine, if I pause this at any moment in time, like here, and I come to this point at 4.5 right here, notice that it's at the exact same location as the point at x equal to 0. Does that make sense? It has the same height, right? Doesn't matter when we stop it. I come to this point right here. Maybe it makes more sense to like shift this down a little bit. That right there, it's at a minimum. This is at a minimum. And why is that happening? What's the reason for that? How far apart are those 2 points? What do we know about the distance between this point right here and this point right here? Find a better place to stop it. What do we know about the distance between those 2 points? What is that distance? It's one wavelength, right? It's also one period. Exactly. It's both of those. It's both of those, right? It's one wavelength and it's one period. Right? They're separated in space by one wavelength. They're separated in time by one period, right? Yeah. So that's effectively the idea of what we're trying to argue right here. The motion, right? Remember that this describes motion. It doesn't just describe distance, because it describes what that point is doing, right? That point on the left is going up and down and up and down and up and down, described by a cosine function. But if we come to some new point x, and we want to know when it has the same motion as the point at x equal to 0, then that's going to happen at a time of t minus x over v, where x is the distance between the points, v is the velocity, and at that time they're going to have the same like shape, basically. So what we can do is we can basically take this time right here, and we can plug it in for the time here, so that we get the following expression. So we take the original function, which was a times the cosine of omega, and then we just plug in this time, t minus x over v. Because the function y is periodic, and there are going to be, at any moment in time, there's going to be multiple points that have the same y value, and you need to have that repeat itself regularly, and that will work to do it there by plugging in for t minus x over v. Okay. Before I keep going, because I feel like that explanation is really complicated, and there are other ways to explain this. This is the way that your book chooses to do it. Other books do it in other ways. They're usually pretty confusing. I tried to do my best there to explain where that came from. But if you do have any questions, feel free to ask, and I'll stop for a second. If there's no questions, we'll just keep going. So what we're going to do here is we're going to use some properties of the cosine function first to rewrite this in a way that's, I don't know how it's normally written. So the first thing we're going to use is the fact that if I have the cosine of negative x, that's equal to the cosine of x. So in this function right here, we can invert these two. So we can write it as I think I want to multiply the omega. No, let's just do let's not, I don't want to skip too many steps. So we're just going to invert these two. And then we're going to kind of multiply some things through here. So we want to write this. How do we want to do this? So let's go with just expanding it out. So you end up getting omega times x divided by the velocity minus omega times t. Now, omega divided by velocity, what's that equal to? So omega is equal to 2 pi times f. So omega divided by v is going to be equal to 2 pi times the frequency divided by velocity. And up here to the left, velocity is equal to wavelength times frequency. So this ends up being equal to 2 pi divided by lambda. That's what omega over v is. Okay. And omega is also equal to 2 pi divided by the period. So a couple ways we can write this. One way we can write it is a times the cosine of omega over v is 2 pi over lambda. So we could write this as 2 pi times x over lambda. And omega is 2 pi over t. So we could write this as t over t. And they both have a 2 pi. So this is one way you can write this. It's not really the usual way it's written, but that's one way you can write it. To where you can kind of see that the x stands over the wavelength and the t stands over the period to give some sense of kind of how the units work in this equation. Because anytime you take a cosine of something, the thing you're taking a cosine of has to have units of radians or units of degrees or whatever. The other way to write it, what I think is the more common way of writing it, is for a traveling sinusoidal wave, we often write it like this. And for this, we have to define something new. So what we do is we say 2 pi over lambda, we're going to give that a name. That's called k. This is what's called the wave number. It has units of radians per meter. So it's like the version of omega for distance. This is your most kind of general version of the sinusoidal traveling wave. So we call this a traveling wave. And in this case, it's a sinusoidal traveling wave. It's a special case of the general traveling wave, which could be represented by a pulse. And we'll talk about one of those here in a little bit. We could also make the wave travel to the left. This would be a traveling wave that goes to the right. This is something you may remember from your math classes, right? That if you shift a function by putting a minus sign, right? For example, if I have a function like x squared and I compare that to a function like x minus 3 whole squared, this function has just moved to the right by a distance 3, right? So with the minus sign in here, it means that you have a wave function that moves to the right. And if you want to get a traveling wave that moves to the left, you just put a plus sign in there. So this would be one that travels to the left. Do y'all have any questions? Okay. Should we do one of these problems, or should we just take a break right now? We can probably do this problem. We can start it at least. All right. I'm going to give you all a chance to kind of read this, and then we'll go through it. Okay, hopefully you've had enough time to read it, at least the statement of the problem. So what we have here is we have Cousin Throckmorton, who I'm pretty sure has shown up in a whole lot of the problems in this textbook, is holding a string, and what we know is that he's oscillating the string up and down, and at time t equal to 0, his hand has a maximum positive displacement and is instantaneously at rest. So that implies that his hand is at a maximum, and he is oscillating this wave on a string so that it carries a sinusoidal wave along the string. We know that because it says that he's moving his hand up and down sinusoidally. We also know the frequency at which he's doing that is 2 hertz. So he's oscillating this up and down at a frequency of 2 hertz, and it's sending a traveling wave along this clothesline, and it's saying the clothesline basically goes on forever. It doesn't get reflected back. Assume that no wave bounces back from the far end. We know the wave speed. We also know the amplitude is 0.075 meters, just to remind you what that means. The amplitude, again, is the height of the wave. So this is the amplitude from here to here. That's what we call the amplitude A. And in this case, A is equal to 0.075 meters. All right. Well, it says to find the amplitude. We obviously just did that. We want to find the angular frequency omega, the period t, the wavelength lambda, and the wave number k. Okay, these are all very simple things to calculate. Angular frequency omega. We have frequency f. Omega is equal to 2 pi times f. So this is 2 pi times 2 hertz. So omega is going to be equal to something like 4 pi radians per second. To find the period t, t is equal to 1 divided by the frequency. These are things that you just, I guess in physics, these come up so frequently, you kind of just gotta memorize these things. Or it helps a lot to memorize them. So this would be 1 divided by the frequency, which was 2 hertz. So this is going to be 0.5 seconds. Period's always measured just in seconds. That's the time for one revolution or one oscillation. The wave number k, she's a different color over here. K is equal to 2 pi divided by the wavelength. To find the wavelength, though, the wavelength is equal to the velocity of the wave divided by the frequency. The velocity of our wave was 12 meters per second, divided by the frequency, which was 2 hertz. This is inverse seconds, which will cancel out one of those seconds. 12 over 2 is 6 meters. So that means the wavelength is 6 meters. That would be the distance between here and here. That's the wavelength. K is 2 pi divided by that. So this is going to be equal to 2 pi divided by 6. So this is going to be something like pi over 3 radians per meter, which is the unit for K. All right, that's part A. Part B says to write a wave... I'll stop for a second. Anyone have any questions about part A? Part B says to write a wave function describing the wave. So for this, we can just use the expression we got in the previous section. So y of x and t is going to be given by a times the cosine of kx minus omega t. So we just plug all these things in. So 0. This is a lot like it's a lot. Oh wait, I'm thinking of my other class. This is a lot like AC circuits, is what I was going to say. Anyway, so 0.075 times the cosine. See, k is pi over 3. And omega is 4 pi. I really should have put the units in here, so we'll just put 3 meters down there. That's it. That's the function, right? Yeah, so that's the wave function. This tells you at any point, at any time t, what the wave's doing or what it looks like. Pick a value of x and then, yeah. Write equations for the displacement as a function of time of Thraki's end of the clothesline and of a point 3 meters from the end. So for part C, if I want to write an equation for Thraki's end of the clothesline, what do I need to change in this equation here? Or what do I need to plug into this equation if I want to find the wave function for that end right there? Yeah, let x equal 0, exactly. So this would just be y of 0 and t, which is going to be equal to 0.075 meters multiplied by cosine of... So if x is equal to 0, we just get cosine of negative 4 pi t, but that can just be written as just 4 pi times t. Because the cosine of a negative is just a positive. So there we go. And now we can actually check to make sure that we did something right here. So it specifically said that Thraki's end has maximum displacement, and it's positive, and it's instantaneously at rest. So we can check to make sure this makes some kind of a sense here. If we plug in t equal to 0, right, this was at t equal to 0. If we plug in t equal to 0 right here, we're going to get cosine of 0, which is 1. So we get y of 0 comma 0 is 0.075. So we knew that was right. If in your homework, for example, that they give you a question where it says something like, that it has maximum negative displacement, then our function would have to have a negative sign in front of it. If it said that the rope was at the center right here, we'd probably have to use a sine function to describe it, or we'd have to shift our function by pi over 2. So in general, you can have, like, a more general form of this wave equation actually would be to, inside of here, I don't know why they don't mention this in the book, but they don't. I guess I should just mention it to you. If you can put a phase shift inside of here. This is the more general version of the equation. In our problem, we know that the phase shift is going to be 0. And that's because of the kind of boundary condition they gave us, that at t equals 0, maximum Okay, I'm going on and on about this, but I think you all probably understand this well enough to understand what I mean, I hope. The information of the problem is kind of going to define what this phi is, basically, is what I'm trying to say. Or whether you use a cosine or a sine. As long as you write it like this, you can always use cosine now. All right. We're also wanting to write the point 3 meters from that end. So that means we need to write down the function for 3 comma t. So that's going to be, again, 0.075 meters cosine of... Okay, so we plug in 3 meters here. We're going to get pi minus 4 pi. And there we go. That shows that the point that's 3 meters away, which would be this point right here, that point right there, should be phase shifted by pi, which means that when t is equal to 0, you get cosine of just pi, which is going to be -1. That doesn't actually work out, does it? Wait. Cosine of pi is not -1. What's cosine of pi? It is -1, right?
Yeah.
Did we get the wavelength right? The wavelength is 6 meters. So 3 meters should be... Oh. Yeah, that's 3 meters. Sorry. Okay, this would be 1.5 meters, I'm sorry. Okay, that makes more sense. Yeah, so this point right here would be 3 meters. And that's the point where the wave is at its minimum. So yeah, that's right. Because cosine pi gives you -1, so yeah, it works out right. Okay. That's good. Okay, does anyone have any questions? Okay, we should take a break because it's 11:05. We'll take a break until 11:15.